Hello, everybody. Welcome back. Please finish your conversations, or at least please keep them like not too loud. Okay. Thank you for coming. This is our last discussion before the midterm one. Yes, and this is plan for today. We'll just do example number one that covers kinetics of system of particles. This is our topic of today, and I think that was a topic of Professor Sonny lecture yesterday. Yes, and then we will do midterm one review very briefly. So I hope you came with some questions. If you didn't come with some questions, you can still think about them, and you will be free to ask them like in 20 minutes or half an hour. We will see. I had like 5 or 6 interesting questions last hour. Yeah, so we'll see. Okay, when it comes to info session, homework 4 is ungraded. Exactly, nothing changed from Wednesday. However, I strongly recommend you to look at that homework and just try to solve these examples just for sport. Yeah, just for practice. There is like 8 problems there, I believe, like 8 problems. Yeah, so we can just do, I don't know, 2 of these and 2 of these. If you have more time, you can do all of them. Yeah, just to see if you want to train kinetics. Yeah, before Monday. Okay, this is midterm content. So it's gonna be kinematics and kinetics of particles. So everything from the beginning of the semester till today, including today. Okay, everything till today. Midterm 1 is held on Monday, October 11, from 7:15 to 8:45 in Biochemistry Building, 420 Henry Mall. I would like to say something. There are three different biochemistry building. Please make sure that you go to the right one, okay? And last names from A to Q are in this room. So it will be like 180 students there. And there will be like 70 students or 80 students in this room. Yeah. By the way, I am proctoring in this room. I will be there on Monday. Yeah. In here, I don't know who will be there, but probably somebody better than me. Okay, that's all when it comes to intro. Any questions? Have I forgotten about anything? So I just want to wish you good luck on Monday, guys. Okay, and I will keep my fingers crossed for you, of course. Yes, and I don't know, just make sure that you study. Make sure that you don't study till like 7 p.m. on Monday. Okay, just be ready like on Sunday. Then have a nice sleep on Sunday. Yeah, wake up fresh on Monday. Yeah, don't party too much. Maybe during the weekend. Okay, actually you can party as much as you want. But you know it's your responsibility. Yes, don't exaggerate with you know what. Okay. Okay, example number 1. Yes, let's do it. Please familiarize yourself with the problem statement before we start our solution. Alrighty, so what do we have in here? Yeah, indeed, we have system of particles, yes, because we have two bodies this time. We have body A and body B. And they're connected with an inextensible rope. And I believe that we know masses of these bodies. Body A and B weigh 5 and 6 pounds respectively. We know that between body B and ground there is a kinetic friction with mu k equal to 0.3. And we also know that at time instant 0, our velocity of body A is 4 feet per second. Yep. And they ask us to find velocity of that body 2 seconds after. Okay. They ask us to find what will happen 2 seconds after. Any questions to the problem statement, or everything is clear? I think it's clear. Okay, solution. Since we are in kinetics, part of our semester, I am not going to surprise you guys that our first part of the solution will be FBD, right? FBD for body A. So we will model our body A as a particle. So this body, yeah, this is body A. We're gonna model it as a particle, and we will just express it here as a rectangle. And KD, I'm going to draw exactly the same rectangle in here. So there are two forces acting on our particle, right? Mg, actually Mag, and there's also tension, yeah, in the cable, T. Okay, and when it comes to KD, let's show our inertia forces here. Let's say that this direction is positive, okay? So it will be MA, AA. All right, that's it when it comes to FBD. And I see that there was a question, Christina. No, this is not possible. No, I'm kidding. Okay, sorry. Yeah, no worries. By the way, Christina, these problems are on Canvas. Did you know that? You can just download the PDF where you have this drawing already, and you have this problem statement already. Yeah. So no worries. Yeah, it can save some of your time, I believe. Yeah. And printer does not cost much money. Yeah, a couple of cents, I believe. Okay. So what's the second step? EOM. Oh, sorry. So we will just write sum of forces, and I believe that that was our positive direction. So we will have in here Mag. I keep forgetting that subscript. Mag minus T is equal to MAAA. Okay, and I think that we cannot do anything else. Yeah, we have only one equation here. So let's count number of unknowns. One equation, and how many unknowns? How many unknowns? I believe two unknowns. Yeah. Not good. Yeah, we need more equations. Okay, let's draw FBD for the other body. For the other body, maybe this will solve the problem. FBD for body B this time. Okay, and body B looks like that. Yeah, and on KD we'll have exactly the same rectangle. Okay, so I'm gonna go for the easy forces acting on the body. There is MG, MBG, of course, yeah, and also normal force. Yeah. Are there any other forces acting on particle B? Calvin? Tension. Okay, so what shall I write in here, Calvin? Yeah, so this is fine? No. But let Calvin say. Yeah. It will. 5 seconds. It's wrong. What's wrong with that T? And I'm gonna go for gentleman. I forgot the name. No, it's Lars. 2T exactly. Look, Calvin, it's actually 2T because we have that pulley structure here. Yeah. This is a very common mistake, by the way, on the exam. Yeah, that's it. We have two forces pulling. Calvin, check this out. Yeah, we have 2T in here. Yeah, so you can guys either leave it like that, like fine. You can leave it like that. What's going on? Sorry for that. Yeah, I'm back. Sorry. Like that, or you can just write in here just one vector that is equal to 2T. Okay. Okay, our inertia forces, MB ABX, and let's say MB ABY. Why not? Okay, right away. What can we say about ABY? 0. And why? Exactly. Due to kinematic constraint, which in this case is ground. Yes? Due to kinematic constraint. Yeah, this is our trajectory of that particle. Yeah, trajectory. That particle cannot leave that plane, basically. Yes? That's why acceleration has to be 0. Oh, so if this component is 0, I bet that we can set up ABX to basically AB. Yeah, our AB vector is aligned with ABX. Great. So we are done with FBD, we are done with KD. We did a little bit of kinematic constraints, so we can put EOM. EOM, sum of forces in the x direction, where this is positive, and sum of forces in the y direction, with this direction as positive. So what do we have in here? Aha, we will have 2t minus tf, and this is equal to mbabx. And in here we will have n minus mbg, and this is equal to, excuse me, mbaby. But you guys told me that this is 0. You guys told me that this is AB, so I can write in here MBAB, and I can write here 0. Okay, so we found one information right away. From this equation, we can see that N is equal to MBG. We might use it later. I don't know, we will see. All right, we cannot squeeze anything from second body. Yeah, we cannot squeeze anything from there. So let's recap. Let's see where are we at. Let's recap. So we ended up with this equation earlier. Yeah, and now we have these two equations. I have these two equations, and you guys told me that this is MBAB, and this is 0. So from here, we just know that N is equal to MBG. Okay, so we have two equations, yeah? Equation number 1 and equation number 2. So we have two equations this time. And I'm wondering how many unknowns. AB is unknown for sure. And I'm afraid already that TF is unknown. Dang, so it's like worse than it was before, yeah? We make it even worse. So we have two equations and 4 unknowns. Okay, but we should not give up, never, yeah? So we need more equations. And I need some volunteers, guys. Anybody has any idea? And it would be AJ.
The TF is force through friction, right?
Yeah.
You could find the friction force with the normal and the...
Sure. AJ, are we in kinetic or static regime? Kinetic friction or static friction? Kinetic, exactly, because that thing is moving, clearly, yeah? That thing is moving with velocity b. Perfect. So we have kinetic friction. Kinetic friction. So we have first equation, Tf is equal to mu k n, and this is equal to mu k mbg. Perfect. We need still one more equation, yeah? I know that you know. I want somebody that was not talking at all. Oscar, do you want to go for it? Exactly. Perfect, thank you. So I will put it in like more dynamics words, okay, if you don't mind. So I would go for kinematic constraint. Exactly, yes. Thanks, man. Kinematic constraint. Which in this case, as you said, is inextensible rope. Okay, so let me scroll up the board, guys, okay? So let us look at that rope. So we have one chunk of the rope in here, and we have two chunks of the rope in here. Yeah. So that means that our AA is related somehow to our AB. So that means that either AA is twice larger than AB, or AB is twice larger than AA. Which one of these sentences is true? Anybody? Where should I put 2? I should put 2 in here, or should I put 2 in here? Based on this drawing. Ben? 2 by AA. Here? Unfortunately not. Yeah, you know, check this out. This is only one rope, you know. So if we pull this rope, look, Ben, do you know how I know that it was wrong? But don't worry about it. Yeah, if we pull this rope down by 1 foot, that means that this guy will go to the right by half a foot. Yeah, so this guy goes twice faster than this guy. Yeah, so actually 2 should be here. Yeah, or 1/2 on the other side. Yeah, so either 2 in here, 1/2 or 1/2 in here. I don't like fractions. I like integers. So this is correct. Okay. No worries. You still have 3 days till Monday to figure that out. And you already figured that out, yeah? So thanks to our little conversation with Ben, we found our fourth equation. Okay, that's it. That's all, yeah? So we all of a sudden have not 2 equations, but 4, and this is solvable. That's it. Dynamics stops here, guys. Yeah, and algebra starts. Yeah, yeah. You ended up with a defined system of equations. Yeah. Okay. Solvable. So at home, solve for AA. Solve for AA. And I did it yesterday with some algebra skills I apparently still have. And I ended up with such expression. AA is exactly equal to 2 times G in the numerator 2MA minus mu K MB, and this is divided by 4MA plus MB. Okay, please observe, this is what you should obtain at home. Please observe that every single quantity on the right-hand side is constant. Yep, that means that our acceleration is constant as well. And we like that, yeah? Plug in values, and you should obtain that AA is approximately 20.310 feet per second squared. Okay. This is not what they ask us for. Yeah, they ask us to find velocity. But before finding velocity, are there questions to what happened on the board? Yeah. Any questions, guys? Okay. So let's find that velocity. Since acceleration is constant, you know what to do. Yeah. Let's just, you can integrate or you can just remember the equation. Yes. So since acceleration is constant, our expression for velocity A is following: VA0 plus AAT, or VA of t is equal to 4, because this is what they told us, plus 20.310 t. So approximately that much. Yeah. Okay, and they ask us to find VA at time instant 2 seconds. Is it better? Yeah. Times 2. Grab your calculators and obtain that our answer is approximately 44.6214 feet per second, and our particle goes down. Oops, sorry. It points down. Yeah. Okay, that's it. Questions? So those systems of particles are easy, yeah? Easy points on Monday, yeah? Hopefully. I don't know. I didn't see the exam. We'll see what's there. And your name is Ian. Ian, yes? Yes, okay.
So, I think everybody remembers the doesn't matter. But what is matter?
So in that case, I will just put minus here and plus in here. Is this what you're asking for?
Yeah. Okay. So
Yeah, so it's still equal to 0. Yeah. Yeah. Also, you don't have to ask me. How about you solve it at home, solve that problem at home, and just flip that vector. And let's see what will happen. Look at it at home, yes? But I choose this one. Any other question? Okay, guys. So what? Review of the exam? Review for midterm 1, yes? Let's do it. I don't like reviews because I usually don't know what to talk about. So I prepared such review, okay? So this is equivalent to what Professor Sonny asked us to do because he sent us like a PowerPoint presentation, yes. However, I found it very useful in this course to summarize you guys what we did week after week, okay? So I would just say week 1 we did that, week 2 we did that, okay? And I don't know, guys from last hour, 1 hour ago said that it was okay. They liked it, yeah. So I'm gonna do it. I got a good review, so I'm gonna repeat it, okay? Okay, so this is our midterm 1. And I'm just going to material covered so far. So what do I mean by material covered? We talk midterm 1 is in kinematics and kinetics of particles. Okay, so I just divided this board into 2 major points. Number 1 is kinematics, and number 2 will be kinetics. Yes, everybody is very surprised by that division. Yes. And in point number 1, I just specified 5 subpoints: A, B, C, D, E. I will just talk briefly about each of them. Okay. So what did we start with? Week number 1. Do you guys remember our first discussion? Like a very first discussion? Everybody besides you. By the way, yeah, because we have a new student here. Yes, actually, we have 2 more new students. Yeah, that came here. So yeah, we talk about elementary motion and 1D motion. In other words, we said that our position, velocity, and acceleration can change in time. Okay, so our S can change in time, our velocity can change in time, and our acceleration can also change in time. Yes, and we can describe the motion, or we can figure out what the particle is doing based on these formulas. Yes. So first of all, first definition: velocity is first time derivative of position. You all know that, yes, in 1D motion or in elementary motion. Then we also know that this formula is useful, acceleration, as a first time derivative of velocity when A is given as a function of time or A is given as a function of velocity. So if you guys see a problem where this is given, go for this expression to solve the problem, okay? However, sometimes our acceleration can be given as a function of position. Yeah. In this case, I hope that you remember our little trick. Yeah. Do you remember that? Yeah. So if you see this expression or this type of expression, go for this formula. Okay. That's all I want to say about it. Yeah. Or our acceleration can be constant, and this is like the happiest day of our life, yes, when this happens, yeah, because then we exactly know what to do. We don't even have to integrate, yes. In the previous cases, we have to integrate, yes. Yeah, Tom and Jared. Yeah, if you want to talk, you can leave, yeah, or you can, if you can talk, but just please do not. Can you do it in the way I don't hear it? Yes, thank you so much. Yes. And also, not only I hear it, because look at the distance between us. These people also hear it, okay? I think that they prefer to hear me. Yeah, at least I hope. Yeah, thank you guys. Okay, so if this is constant, you can just go for our ready to go expressions. Yes. Yeah. Okay, so this is basically our first week. Maybe actually our very first discussion. Do you remember? We ended up with that long problem, yes, where velocity and acceleration were not given to us explicitly. Do you remember? We're like very struggling. There was like 2 tricks, I believe. Yeah. So this is our first week. Yeah. So just introduction of the motion and what to do when these things are given explicitly and implicitly. Yeah. Questions? Have I forgotten about something? Is it okay so far? Do you like that review? Okay. So then what we did in the second week, projectile motion. I personally have nothing to add. Okay, I don't want to even talk about it. Yes, we recorded like 2 examples and we killed them basically. Yes, to the tooth. Yeah, we talk about every single detail about projectile motion. Yes, if you want to see these examples, they're on YouTube. Go to week 2 Wednesday or week 2 Friday. By the way, in the description of videos, I usually summarize what the video is about. Yes, so just find the video with the description saying that this is projectile motion. Okay, I have nothing else to add. Yeah, unless you guys have some questions. Okay, then kinematic constraints. So what did we learn today? Inextensible rope, we talked about it even today, yes? So you guys know what to do when there is inextensible rope, yes? We did it even today. Ground, it was also in that problem we finished 5 minutes ago, yeah? You guys know what to do when there is a ground. And also I think on Wednesday we had rod, yeah? So we had a collar on the rod, yes? So there was, that caused like some constraint in the motion, plus I think that the normal force was like pointing perpendicular to the rod and also out of the paper, yes, or into the paper, yeah. Yeah. So these are kinematic constraints we learned. Fourth one, I don't remember any fourth one. Yeah, maybe there will be some fourth one. I don't know. You will figure it out. Any questions about kinematic constraints? Because this is also what we covered here. Yes. Relative motion. So what? So just remember that our acceleration of one particle can be expressed as acceleration of another particle plus relative acceleration between them. Okay? And we can do exactly the same when it comes to velocity. So VB is equal to VA plus VB relative to A. Yeah, we also talk about that. And now everybody's favorite, description of motion in different coordinate systems. Yes. So we learned 3 different coordinate systems. Yes. We learned Cartesian, polar, and normal tangential. Okay, let's start from the beginning. Let's do it wildly. Let's start from the beginning. So what's specific about Cartesian coordinate system? Nothing really, yes? We just describe the motion in I and J that are constant unit vectors, yes? Constant unit vectors. That's why description of some kind of motions is so easy in this coordinate system, yes? Because we can just, in order to find velocity, we just differentiate each component, differentiate once each component of position, and in order to find acceleration, we just differentiate over time once each component of velocity. That's it. But 2 weeks ago, we learned polar coordinate system, so r theta. Okay? And UR and U theta are no longer constant. Not constant. I'm gonna underline not constant unit vectors. Okay, and UR is always aligned with position vector, okay? And if we differentiate over time once, we'll end up with this expression, okay? And then if you differentiate over time for the second time, we'll end up with this expression. And these guys will be given to you on the page with equations, yeah, during the exam. Okay, I have nothing else to add. And when it comes to normal tangential, again, UT and UN are again not constant unit vectors, not constant unit vectors. UT is aligned with velocity, and if we differentiate over time once, we'll end up with this expression. And we did multiple examples using these coordinate systems. So I personally, guys, have no idea what shall I talk about during review. Yeah, I just summarize. Yeah, I can even maybe generate a PDF of that document, and you will see basically what you learned so far. Okay, I will send it to you over via email. All right, so everything above this line is kinematics of particles. Kinematics of particles. Any questions to what happened so far? Questions? Maybe one thing, because before going to kinetics, I just want to let you know, guys, that we didn't talk about mass of this particle above that line. Nothing. There is not a single information about how much the body weight. Okay. When it comes to kinematics of particles, we care only about the geometry, and by geometry I mean how the geometry of the trajectory. Okay. So if our particles can move along the different trajectories, yes, and then we can just figure out some different peculiar relations, yes, between like some quantities describing our motion, yes. So in here, kinematics of particles, the only thing in here is that trajectories are different, yes. They can be linear, they can be curvilinear, and you guys should know what to do when you see such problems. Okay. However, last Friday we talked about a mass of these particles for the first time. Yes. So we started kinetics of particles. So if we have a particle that has mass and we have a force, actually net force, acting on that particle, this will cause acceleration of that particle. Yes. And that acceleration will be aligned with force acting on our particle. Yes. Maybe one more thing. So in kinetics of particles, we talk about cause of motion, which is force. Force causes motion. In kinetics of particles, we just knew that motion is happening. Somebody told us, hey, this thing is moving, figure stuff out. Yeah, figure it out. Yeah. They didn't tell us in here, they didn't tell us why it is moving. We just knew that thing is moving. We told us that, oh, this is expression for acceleration. I don't know, find position after 2 seconds. Yes. They didn't tell us what is causing that move. Yes, that motion. In here, we exactly focus on the cause of the motion. Yeah, so force. And what did we do in here? We focused on kinetics of particles in Cartesian coordinate system. And last Wednesday, do you remember? We did it in curvilinear system. Not last Wednesday, this last Wednesday, like 2 days ago. Yeah, we did it in polar coordinate system, and then we did it in normal tangential coordinate system. Yes, so you can for sure expect something like that on the exam. Yeah, at least one problem will be covering this. And today we talk about kinetics of particles, of systems of particles. Yes, so you guys got that problem? Easy points. Yeah. Yeah, and there might be some elements of relative motion. Why not? Okay, any questions so far? Yes, Josh?
Is it common for like the systems of particles to be find like a problem in the textbook or something like that? It's like the system of particles in
For systems of
Yeah.
particles, yes. It's problem dependent. Yeah. So system of particles can also move in the curved linear coordinate system. Yes. This is my answer to your question. Are you happy with my answer? Okay. Yes, they can also move. Yeah. Okay. And now I just would like to finish with solution steps, guys. Okay. So I think AJ, do you remember like 3 weeks ago you asked me how on earth do I know how to solve those problems? Yes, and you asked me, is there like a solution? Are there like some solution steps that I should that we can follow to solve these problems? Yes, so we just wanted to not think much, just wanted to do that point number 1, then point number 2, point number 3. Don't worry, I don't blame you. Yeah. When it comes to kinematics, so the first part of our semester, I don't know. I just go for it. You know, there are no solution steps. However, in kinetics, in the second part of the semester, yes, please follow this recipe, and you guys will solve 99% of the problems. I guarantee you. Yes. So on Monday, if you see that problem is about kinetics, please start with FBD and KD. Okay. Please draw those things. Okay. Please do not forget to draw KD. Always draw exactly how I'm doing all the time. Yes. I did it like 12 minutes ago. Yes. I started with FBD and KD. You will get points for that. Okay. You will get points for that. What's the next step? We did today, EOM. Yeah, just look at your FBD and do not forget about, put there every single force, yes, that act on the body, and not more. Just put every single force and not more. And then look at your FBD and KD and create equations of motion. Then what was the next step today? We just counted how many equations do we have, and we counted how many unknowns do we have. Yes, so this point. Usually, you will end up with more unknowns than equations. So it's okay. What you should do next? Find more equations. Yeah, this is your next step, and you can find more equations. Who said today we did friction? I think Sam, it was you, yes, or it was Lars maybe. I forgot who said it. Yes, you guys told me to go for friction. Okay, I went for friction. We have another equation. Then Oscar, it was you. You told me to look at the rope. Yeah, I went for the rope, and we found another equation. And then dynamics was done. Yeah, and the rest was only algebra. Okay, so guys, just follow these 5 steps, and you will be good. Yeah, just follow these 5 steps, and you should be good on Monday. Okay, when it comes to kinetics, at least. That's it. That's my review. Thank you for listening. Yeah. Do you have any questions? Yeah. Or did maybe I forgot? I forgot about something. Yeah. Have I forgot to cover anything? Yeah. Okay. So mic is yours right now, and we have like 10 minutes. Yeah. Mic is yours, guys. Any questions? Yeah.
You say you're going to put this on Canvas?
I'm not gonna put it on Canvas. I'm going to send email to my students. Yes. Yeah. Can I have attendance, please?
Yeah.
Here. Okay, guys, you don't have questions, really?
Yeah.
So you are Drew.
Yes. So you said for like the R unit vector always goes along with position vector. I forget. Is there like a way you line up the normal and tangential too? Is there a certain like rule like that or like the normal somewhere?
So I must go back. I actually do not understand your question. So wait a second. Your first part of your question was, yes, I agree with you. R is always aligned with position vector. Yes, you can see it here. You can see it here. UR is always aligned with R. Okay, that was your question, yes? First, yeah. So yes, R is aligned with UR. And your second question was about
I guess it
what?
would just be like, can you like quickly go over again like how to define the coordinates for the normal and tangential? I guess. Is it like pretty arbitrary, or is there kind of a rule like that?
I would not say that it's arbitrary. I see you, Lars. Don't worry. I see you. You can put your hand up. Yeah.
I think I know what I'm talking about, like the direction normal,
Yeah.
so it's like the direction to
Inside the curvature, yes. Yeah, you can go for it. Yeah, talk more. It's fine. I see. So yes, okay. So I see right now. So yes, UN. So this is normal tangential. So UN always points inside the curvature. Okay, UN always points inside the curvature. You can see that it flipped. Look, Drew. We started at time in here. We started here. Oh, what's going on today? Yep. And UN points inside the curvature, yes? And then our point moved here, and UN flipped, yeah, the direction, yeah? But it must still point inside the curvature. However, so this is NT coordinate system. However, when it comes to polar coordinate system, we just define UR that is aligned with R, and U theta is always on the left-hand side of UR. Or U theta cannot point this way. It cannot point this way. This is incorrect.
So could you go in either direction?
No, because UT is defined positive V. Sorry, V is defined like that. UT positive V. There is no minus here. No minus here. You see? There's no minus. Yeah, it's always plus.
So it's always going to the right then, or?
It's always aligned with velocity. If your velocity vector, yeah, so if your velocity vector points this way, your UT must be pointing this way. Is this okay answer?
Yeah.
Yes. Okay, guys, I am open for more questions. Yes, Ian?
First, there's some of like this the free body diagram and diagram versus
Yes, that's why we call it free body diagram. Because it's free body. That body has no idea that there is that this body has no idea that there is another body in the system. Okay? We just that body only knows that something is pulling it, but it does not know what it is. Yeah, it can be like, I don't know, giraffe or something. I don't know, elephant, whichever you want. Yeah, and also this body just is free. Okay, so on that drawing, that body even does not know that it is on the ground, because we replace ground with a normal force. Okay, we free it from constraints. Actually, in my native language, term free body diagram does not exist. Can you imagine that? That's strange, yeah? We call this freeing from constraints, yeah? We replace constraints with forces, yeah? I think that was your question, yes. We don't do it for the system. In kinetics, we consider each body separately. That's the answer to your question, yes? Later this semester, it might change, okay? But so far, each body separately, okay? Okay, good questions. Yeah, I like it. And I'm not saying that because they told me. These are good questions, yeah? Yeah. Okay, do you know that there's like a training for TAs and they tell me that always price the questions. Like, no, I don't try to be nice. That was a good question, yeah. Yeah, it's okay. Anybody else? I see, guys, that you really want to go, like, especially you. You really want to go. Christina, yes? I have 5 minutes. This is like the hardest thing to do. Yeah, this is like the hardest thing to do. Yeah. Really? No, but you're able to understand it. Yeah. You know what? Actually, 1 hour ago, somebody asked me how to switch from polar to Cartesian. Yeah, I can repeat it for you right now. It will take me. We have 5 minutes. It will take me 5 minutes. Do you want me guys to do it? Yeah. But I see, guys, that half of you would like to go. So let's do that. If you don't want to stay here, you can go. Okay? And only people who are interested in that they can stay. Let's do that. It's your choice. Okay. Then we are going to continue. Okay. So. Okay, Christina. So we will go from polar, from r theta to Cartesian. Yeah. If we really would like to torture you on the exam, and I think we don't want to, we will ask you to go from polar to normal tangential. But I think we are, I mean, I don't know, I'm pro student. I don't know about other guys. Excuse me?
The practice exam had us doing that. Normal tangential to polar.
They did?
Yeah.
Ah, you see? Bastards. These guys are bastards. These guys are bastards, you see? Yeah, yeah. Really, okay. So we would like to end up in this coordinate system, J and I. And let's bring velocity, okay? So let's say that our velocity is maybe here. Oh. Okay, this is our velocity. And Drew, check this out. I'm drawing a position vector because particle is here. Yes, this is our R. Oh, shoot. This is our R. And this is our UR, okay? Always. And this is our U theta. And this is our theta. Okay, this is our theta. So you guys can clearly see that so how to express velocity in, let's say, r theta k. So I have to just do these projections, right? On these green projections. So this big projection, let's assume that this is like 100, okay? 100. I don't know. And this one will be 5. Okay? So in r theta, I believe that our vector will be following. -5, -100, 0. Yep. This is exactly vector expressed in this green coordinate system. Blue vector in green coordinate system. But Christina asked me to express exactly the same vector in I and J. Yep. I, J, K. In this coordinate system. So I have to bring that vector to this coordinate system, to that red one. Yeah. So I would do it like that, Christina. I would, first of all, project this 100 on these two directions. I would go here and here. Okay? And I think that we need this theta somewhere here. Yeah, we need this theta somewhere here. Let me bring it there. So if theta is here, I bet that 90 minus theta is here. Yep. And I bet that based on that, theta must be here. Must be here. Okay, Christina, this is 100 sine or cosine theta. Take your time. This is perfect. Yeah, it's sine. Sine theta. And this one has no other choice. It has to be cosine. Exactly. 100 cosine theta. Okay, 50% of the problem done. So now that little guy, let's do it in orange. Oh, shoot. It's already 10:50. Guys, can I steal 1 minute from your time? 1 minute, 60 seconds, okay? I'm very sorry. I shouldn't do it. I know that I shouldn't do it. Okay, so we just also have to project this little guy, okay, on this direction and this direction. And if 90 minus theta is here, theta must be here. Okay, so this little guy will be 5, I believe, cosine theta, and this little guy will be 5 sine theta. Okay, we're done with projections. Now we must go back here and we must write red and orange vectors here. So red guy will be 100 sine theta, because it points this way, minus 5 cosine theta. This is our x component, and y component will be 2 negative. It will be minus 100 cosine theta minus 5 sine theta 0. That's why I bring one vector from one coordinate system to another. Okay, indeed 60 seconds. Guys, good luck on Monday. I will keep my fingers crossed for you, okay? You will do good. See ya.